All right, good morning, everyone. Okay, so here's a little thing. I need you guys to try to be on time, okay? Because as you can see how Zoom works is there's a waiting room, and then once you get in there, they're gonna send me like a permission to admit you in. I cannot guarantee that I'm gonna look at the invitation, so-called, when I start. It's really important that you get here as early as you can. That way I won't have to be stressed out. Hey guys, yeah, so I don't have to be stressed out and multitask like I am doing right now as I'm talking. There's some people that I'm admitting, so please just pay attention to the time, okay? All right, so go ahead and tell me how you felt about last week's quiz. What was wrong? What was hard with it? Did it throw you off just because of the bicyclics or? Okay, so some of you guys were okay, but for the majority, I think you guys kind of felt like you were you got popped off, right? So hopefully, I don't know if this is gonna be the standard going forward, because technically now it's gonna be open book. But here's the thing, I need to cover all the material with alpha carbon chemistry because it's gonna be a big part of your exam 3. So I'm not leaving anyone behind with that. Yeah, I know this week is gonna be 2 quizzes combined, so there's definitely gonna be some amines in there, which means that after I finish alpha carbon and after I finish going through some of the quiz questions, I'll stay behind for questions pertaining to amines. Okay, I might just go through the simple Gabriel amine synthesis mechanism just because it's quite a popular reaction, especially on quizzes. So I might go through the concept for that. So for your Melina students, so you don't have to worry, or at least for all of you, because your Melina's class did not go through like the Buckwald-Hartwig. They did not go through the Hoffman elimination, did not go through the Paul-Knorr. So if you guys have no idea what I'm talking about, chances are it's not going to be on the quiz, okay? How is it going to be 2 quizzes? So you're going to have 2 predicting the products, 2 predicting the reagents, 1 mechanism, 1 retrosynthesis. That is what I understood correctly? Okay, so this week's quiz is primarily on problem set 10, which includes, which starts from Dieckmann condensation, actually, just right about where we left off. And also, what is on this week's quiz would be, so I did go a little bit faster last week with enolates. You will have to see, you will see stuff like the malonic ester synthesis. So please go through that, right? You guys can see my screen, can you? Okay, cool. Yes, I am recording it, don't worry. So this week you can expect to see, oops, malonic ester. You can expect to see, pay attention to acidic and basic conditions, okay? Be very careful. If you, honestly, since it's open, but just have my notes with you, right? The answers are sort of there. You're gonna see alpha halogenation because Dr. Molina, she ended off alpha carbon with this topic and the haloform reaction. So these 2, you can expect to see them there. I have not seen the quizzes, but this is what I'm guessing. Okay, so don't quote me on that word for word, but I am just guessing that since there are going to be 2 topics, you're going to have all these stuff from alpha carbon, and you're going to have a little bit from amines. But the good thing about amines is that there are only 2 main reactions that you need to worry about, because Dr. Molina's class have to already only covered up to alkylation. All right. Can you guys hear me, by the way? Okay. All right, so for those who are streaming in right now, please take note. Come in on time if possible. Come in before. That's what the waiting room is for. Please, don't come after or on the dot at 7 because, like I said, once I start, I cannot guarantee that I'm always going to look at the participant list or like the invites to bring you into the room, right? The only exception that I usually make is if you get kicked out and then you're going to come back in, right? So I really appreciate if you guys could come on time from next week onwards, okay? So also, okay, more announcements. This week's quiz continuing, you might see stuff like the Dieckmann condensation, the Claisen condensation, addition to alpha, beta, and saturated, which is basically microaddition. So if you remember that concept of microaddition, it's quite a big topic in itself. It's just a 1,4 addition, right? And the Robinson annulation. So I'm gonna cover all of this today. Yes, it's being lecture captured. I will send you all the links by default after class. And okay, so you don't have to email me anymore because I've been getting like tons of email every day. And I just decided that we're at this point of the semester, given our circumstances, I honestly don't care about what other people say. Like if they wanna, if they have an issue with me sending you the link, then I'll deal with them. But I also trust that you guys do not like circulate the links without my permission, because technically I'm doing something that is not according to guidelines, right? I'm just going behind the loop for you. So please help me to help you. Okay. Second thing, yeah, so amines, I think, like I said, you can only expect Gabriel amine synthesis and the alkylation reaction. I don't think your Molina's class even did the mechanism for that, so you're off the hook. But you need to know why we need the amine synthesis, okay? Yeah, I don't know why some of you are having audio issues, but you probably have to check your audio settings, okay? Do you guys hit join audio? It's like when you come into the room, right? Yeah, exactly. Yeah, so the reason why I'm using Zoom is because your professors are also using Zoom. I just want to have a commonality in terms of like the online platform. Hope you guys are okay with that. Shoot, I have something to say, but I forgot about it. Damn. Okay, well, I'll think about it if it comes to me, I'll let you guys know. Oh, office hours this week. Okay, so office hours this week are going to be dedicated to all the all the amine stuff. Okay, I will still be working through problems at 10. I will upload the key after the review, and moving, because now we are sort of like a week behind. Unfortunately, I cannot do amines today, like in a formal review setting. I can just answer some questions, but I can do like I cannot do the formal review because, like I said, Dr. Molina's class is way behind. There's no way I can go that far past her. I hope you guys understand. I'm really sorry about it, but I will be dedicating this week's office hours to amines. Okay, it's on Tuesday, Thursdays, 8 a.m. No, 8 a.m. my time. So it's Tuesday, Thursday, 6 to 8 p.m. Okay. I will open up the registration link after this as well. And now, because we are a week behind on reviews, the following week before exam 3, you're gonna have 3 back-to-back reviews. Okay, it's gonna be on Sunday for amines, Tuesday for sugars, Saturday for amino acids, and then Sunday for the exam 3 review. Are you guys all okay with this? Does anyone have a problem? It's gonna be intense. Let me warn you first. But that was just how the circumstances kind of forced it to be. I mean, I used to have it every Sunday, but now I don't think I can do that. At the worst case scenario, I might have to miss one review. Okay, so everything, my timing is all standard. It's all from 6 to 8. Okay, but for this week, it's gonna be for primarily amines. Okay, and the next week would be for mostly reviews. So I'm leaving Thursday open next week for office hours. So let me give you the dates, okay? Sorry, lots of announcements. It's just hard now, just because I don't get to see you guys often. Okay, the 12th, we're doing amines. The 14th, sugars. The 18th is amino acids, and then the 19th is exam 3. If you can't make it for it, I'd say just sign up still, because usually I populate the list and I will send out the email links right after the review. So just sign up to have your name captured in there. Okay. I'm a lot more relaxed with like the policies now. I'm not, just because I know you guys are not having it easy either. Especially if you saw the quiz this week, right? I got emails asking if this was the standard moving forward, and I can say yes, probably so. All right, so it's also a good time to check your understanding. And for those that were saying that they did not really struggle, I noticed that the most of you were actually attending my spring break reviews, so I can see how that's paying off for you guys. I'm really happy to see that. If you guys have not seen those review lecture captures, I've already sent out the email last week. Okay, before I start now, is there any last question? No? Okay. So yeah, I just hope you guys understand on my end with the limitations that I have. I try to accommodate, but if I can't, I do apologize in advance. But I'll try, okay? All right, so let's continue with our discussion on alpha carbon chemistry. We are on reaction number 7, Claisen condensation. Why is it called a Claisen condensation? Why is it a condensation? Because you are kicking off a good leaving group of sorts, right? So usually when you have an acidic proton, right, this is always the first step of this chapter. When you see something with a carbonyl and you see a base in there somewhere, look out for this, the alpha hydrogen, right? Alpha hydrogen gets deprotonated by the base. And don't forget, it's a reversible reaction to form an enolate, right? You need to always have your enolate. If you don't have it, you're doing it wrong. Next, you're gonna find your, you are gonna have to find your electrophile in the form of a diester. Okay, so nucleophile adds to electrophile. Okay, to form this product. Oops. Okay, what do you think is going to happen next? Anyone wants to take a wild guess? Yeah, exactly. You're going to form a carbonyl, right? And then the ethoxy group is going to leave because it's a good leaving group, right? Okay, now what's going to happen next is, don't forget, you need, that's why we have this step, right? When you have an acidic protonation step, that means your base can come back to deprotonate the alpha hydrogen again. Okay, and that is why we need the proton source in the form of ammonium chloride. You might just see you might just see H3O plus, you might just see H plus. The point is to give a proton for the reaction to go to completion, right? And this is the final product. Yes, David, that's exactly right. If you see NH4Cl, know that you need to protonate something. Okay, so you're removing one of the R groups and adding it to your carbonyl, basically. Okay, this is pretty simple stuff, right? Which is why usually the length of the mechanism kind of tells you how hard this is. It's pretty straightforward. It's not too bad. But you have to pay attention. You have to watch out if there are any R groups attached to the alpha hydrogen, the alpha carbon. If there is, right, there is no reaction. Let's see why. Okay, so it's really important. You notice the difference in the top example. I have two alpha hydrogens basically, right? But the bottom, I only have one. So if you only have one alpha hydrogen that you can deprotonate, then it's wrong. Oh, sorry, there's no reaction. Okay, let's see. So same thing happens with the first step. Nothing changes here. I have an available hydrogen there. Right? So this is the first step. And everything as far as Dieckmann condensation works is the same. So we have the same collapsing of the lone pair and adding to my electrophile. Right? Okay, so same thing, formation of the carbonyl to get rid of the first ethoxy group. Okay. All right, but here's the thing. Do you see that? Oops, sorry, I forgot the methyl here. Don't forget the methyl. Right? Do you see that the methyl now is blocking the way of the alpha carbon? Right? There is no more alpha hydrogens there, which means that the ethoxy group that I just kicked off can come back for revenge. Right? To form back the same product that I had in this step here. Okay, and when the double bond, when the lone pair collapses, it has the tendency to cause the entire molecule to leave because, like I said, there is no more acidic proton, so it will not have any reaction, basically. Okay. So what is that? What am I trying to say is that even in this step here, okay, there is a possibility of the for the entire molecule to leave on its own already, right? I'm just showing you that there are many ways that you can do it, but eventually you're gonna encounter this step where the entire molecule leaves and there's no reaction. And yes, Jacqueline, you're right. Yeah, so if you don't have the extra proton, there's nothing to deprotonate, right? So that's why the driving force is not being facilitated and you get no reaction. Okay, so just look out for the extra hydrogen. Okay, so that's the Claisen condensation for you. We are going to go into a subtopic right now called the Dieckmann condensation. So the Dieckmann condensation is a type of Claisen condensation. Okay, specifically what kind is it? It's the intramolecular Claisen condensation. Okay, and what does intramolecular mean? What are you trying to form here? Yeah. I know you guys get scared whenever like rings are formed or broken. So as you can see, this topic has a lot of these, right? So be very careful, okay? So what do we have here? First and foremost, when you have a Dieckmann condensation, you have to be working with an ester. Remember, the proton on a carboxylic acid is really acidic. So when you have a base going in, you are gonna get that proton deprotonated right away, okay? So you cannot, so every time you see a carboxylic acid, make sure that the next step that you're dealing with is gonna esterify your carbonate. If you're not esterifying it, then it's probably a no reaction type of question, okay? Are we esterifying the next step? Yes, this is the Fischer esterification, right? So what we have here is this product here, and then we go up into a ring. Okay, I'll write the answer later after I talk about the mechanism. Okay. All right, so mechanism. Okay, that's that's a really, really long chain. All right, let me start this way then. I'm missing a carbon. Hold on. Ooh, 1, 2, 3, 4, 5. Yeah, I think I'm missing a carbon. Sorry, the placement of the carbon here is wrong. So I'm having an extra carbon there. I'll get rid of that. Sorry about it. 1, 2, 3, 4, 5, 6. Okay, so this is what we have here. I'm just flipping it upside down so it's easier to work. Well, as you can see, this is a symmetrical molecule, right? Oh, so yeah, as alpha carbon is already done for both professors. So this is really a review right now. It's called the Dieckmann condensation. I definitely remember her doing that. So probably want to check your notes if you want to find it there. All right, so both sides of the carbonyl are symmetrical, right? So it doesn't matter which proton I deprotonate. It could be the one on the left, it could be the one on the right. Let's just go left, but in no way is that my political view of anything. So we are gonna get a base, deprotonate the hydrogen, form the enolate, right? So if oops. Okay, now I want you guys to tell me what you might do intuitively. Remember, the point of reviews is for me to teach you to ask questions that you can ask yourself in exams, right? What would Yan do, or what would Dr. Driver? What did Dr. Driver tell me? Or Dr. Molina say, right? So everything that we sort of taught you, yeah, it's gonna go through an internal nucleophilic attack. Exactly. Collapse the the lone pair, form my enolate, right? So what I get would be this here. All right, David, I'll get to it in a bit. Okay, so this red one here is right here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. Okay.
Can we ask a question without like typing it in? Because I feel like it might take a little longer.
All right, so we have an alkoxide here. We need to bring it down into carbonyl. This itself here is a good leaving group, right? It's a good leaving group, so you get rid of this here to form this product. Okay, are we done? Do we attack at the carbon, at the ketone, or the... Jenny, sorry, which carbon are you talking about? The one on the right. Okay, this is step 1, step 2, step 3. Are you talking about step 2? 7-member ring. Let me see. Ooh, okay, let me see. Ooh, 1, 2, 3, 4, 5, 6. No, as you can see, this is 1. Oops. 1's right here. Right, the red one, and then 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yeah, okay, good. So we have that there, and like you guys said, we're not done because we have another alpha proton. And why do you think it's this particular proton that gets deprotonated? Have you ever wondered why? Not just pKa, but think about the base that we're using. What kind of base is Naomi? She's a thermodynamic base, right? So she goes for the thermodynamic proton, basically, which is right here. These are subtle like questions that you have to ask yourself, right? So that it helps you to understand the topic a little bit more in depth. Okay, and that's why we have what? A source of proton. To get me my product here. Oops. This is step 3. Okay, whatever we have been doing is just step 2. Okay. So that is the Dieckmann condensation. Let's go ahead and put our product in there. You guys see what I'm doing here? If you don't necessarily know what the product is, if you're asked to predict the products, draw the mechanism. Okay, so once you draw the mechanism, you should be able to find the answer. All right, why isn't no reaction since there's only one proton? Well, no, because the previous example, you already had the proton right here, right? And you're doing a Claisen condensation with the extra proton, which means now if I were to do this now, yes, then now there will be no more, no reaction. Okay, so ring formation will occur when you have typically two carbonyls on the same chain and then a base coming in, because the base is gonna do this step here, right? It's gonna grab that proton, and after that, you're gonna have an enolate that's gonna attack the carbonyl within the same chain, the other carbonyl on the other end. Okay, so look out for two carbonyls on the same chain. That if you see that most of the time, it's a ring formation. And also, please please make sure that you make sense of it. They usually form how many membered rings? If you had this here, is this going to form a ring? The one in black? No, right? So that's a clue. It would not make sense. So please do not try to form 3-membered rings, 4-membered rings. These are a no-go. Okay, 5, 6, maximum 7. But you're not going to be given more than that, because can you imagine how long this chain is going to be, right? So don't worry about it. Just focus on the 2 carbonyls and you should be good. So I had a question if this should have been H minus. No, because we are starting from a carboxylic acid and we are doing an esterification reaction to give us the ester in there, right? So this here is right here. Okay, so let's talk about 1,4 addition with soft nucleophiles. What are some examples of hard nucleophiles? Does anyone remember? Grignards, exactly. And not, I mean, be more specific. I'm looking for a more specific answer. Organolithium. Okay, so these two are primarily hard nucleophiles. Everything else is soft. So you have your cyano group, your azites, your amides, right? Your Gilman reagents. Thiols, so on and so forth, right? But the most common ones that you might see is a cyano group and the Gilman. Okay, so I'm not going to go into detail when I cut hard and soft nucleophiles in the first place, because this itself is a 1,4 addition, right? So you're only probably like 99% of the time you are going to deal with soft nucleophile anyway. Okay. All right. So what's the first step? We are forming what? Okay. Yes, we are forming a carbonyl. Okay, and then we have a strong base. What's that base gonna do? Are carbonyls far enough to give us a good number of rings? Let's see, we have 1, 2, 3, 4, 5, and 6. So yeah, no, it's actually pretty good, right? Yeah, it's good because we can protonate the one from the methyl. So yes, we are gonna get a 6-membered ring, and I'll show you the mechanism after, okay, to give us this product here. So let me number my steps. Step 1, step 2. And now we get our 1,4 addition, right? Why is it 1,4? Where's the 1 and 4? 1, 2, 3, and the oxygen on 4, okay? Even if the methyl was not there, right, it would be a good, a 5-membered ring, I think. No, that would have been 4. Yeah, so 4-membered rings are not good, but 6-membered rings are. Okay, and in step 3, we have a soft nucleophile going into the 1,4 position to give us this product here. Oops. Right here. Okay, 1,4. Let's look at the mechanism, shall we? Okay, so first step, I'm going to start from step 2 where we have the carbonyl already. And why do we know to protonate the terminal proton and not here? We could have gotten the proton from here too, right? But why? Why did we choose the one on the left on the end? Yeah, it forms the largest ring, the most stable. Exactly, because if you were to deprotonate here, you're gonna end up with this here. So you are gonna have a 4-membered ring, and that's not good. The one in the terminal gives us a 6-membered ring, and you're gonna see that in the Robinson annulation later. Yes, because nature favors the most number of rings. So I think that trumps everything else. Okay, so proton here, proton. Ooh. Right here, right? We have that methyl there. Okay, so now, do you see that my carbonyls are far apart enough, right? So nucleophile as the electrophile. We have this here and this carbonyl here. Okay, so let me number my carbonyls. Okay, so this carbonyl is right here. Sorry, this carbon is right here. 1, 2, 3. 1, 2, 3, 4, and then the blue one here is 5. Okay. All right, so do you see this alpha proton here? Well, we have an alkoxide, right? And do we have an acidic workup? No. So it's going to find a hydrogen somewhere within the molecule. Oh, you can't see. I'm sorry. Oh, yeah, that's bad. Okay. Here. Okay, let me just be a little bit. I'm going to use darker colors for the next one. It's right here. Okay. Now, like I said, if you do not have a separate step on protonation, right, a source of proton, then the alkoxide is going to look for it internally. Where specifically, it will always be the alpha hydrogen because you want to form what? Anyone? What are we trying to form?
Enolate.
Yeah, your enolate flags, right?
Enolate.
Oops. Yeah, there you go.
Ăn một cái mát của câu 1 hả?
All right, don't forget that. Okay, so once we are done, then we're gonna form our carbonyl again.
Flex. What is?
Yeah, you had a question? Hello? All right, anyway, so let's go down here. Okay, and what happens to the alcohol? It leaves, right? So do you think alcohol is a good leaving group on its own? No, what do we need to push it out? Heat, yeah, so go ahead and write heat here. I forgot to put it in there. And with heat, we are still kind of reversible, but the backwards direction is way more favored because we don't like alcohol to leave, right? But anyway, so heat, then what we have here is R1 for proton, sorry, L1 for carbonyl. So this here is called the alpha beta unsaturated carbon, okay? Alpha, beta, okay? And your nucleophile, your soft nucleophile is always gonna attack which carbon, the alpha or the beta? Even though this is alpha carbon chemistry, but it goes for the beta position. Why? Because of resonance, right? I can draw resonance structures for that molecule. Oh my God, resonance, the very first review topic, right? We're doing alpha carbon chemistry now. So because of that, when I draw it, do you see that the beta carbon now has an electrophilic position? And because of that, my nucleophile, what am I adding here? Thiol ether. Okay, so thiol ether is going to come in, right, to form that product there. Okay, but what we prefer to show would be your 1,4 with thiol ether coming in to form the enolate there. Right, and then what are we doing? We're adding a proton in the form of ethanol. To give us our final product. Oops, sorry. I mean, you could do that as well, but you have to show the tautomerization process, okay? So let's just be simpler and more consistent and draw this product here. There we go. It was, here. All right, okay, so with this example, the same thing works for Dieckmann reagent. We have the phenyl group, which is negatively charged. It goes into the beta carbon. Okay, pushes this up right here. don't forget the protonation step. Sorry about that. Okay, so we have the phenyl group. What do you mean by why is that preferred? Oh, because you're explicitly showing the formation of an enolate through a nucleophilic attack, which is pretty much what we have been teaching you all this time, right? But I'm telling you, I'm showing you that resonance structure to prove to you why the nucleophile would go to that particular carbon, which is the beta carbon, because it induces an electrophilic site through resonance. Okay, so once you pronate it, then what you have for your product is this here. Okay. So don't forget, this is a 1,4 addition. Well, if it's a hard nucleophile, it will go into the 1,2, which means it will attack the alpha carbon instead. So because this topic itself is called a 1,4 addition, so we have to find nucleophiles that will go into the fourth, or that will give us a 1,4 addition, which is the beta carbon addition, right? So that's why we don't really focus on the hard nucleophiles. We actually focus a lot more on the soft nucleophiles. And why do we do that? Because there is something called microaddition. Okay, and what microaddition is when you have a carbonyl and a 1,4 sort of like alpha beta unsaturated again. So pretty much what we saw was soft nucleophiles going into an alpha beta unsaturated, right? Right here we have a carbonyl going with a 1,4. So what do you think is going to happen? Well, we have this thing called a microaddition specifically. And usually the one with the alpha beta unsaturated carbon is called the microacceptor. I don't know if Dr. Driver taught that. Did he use this term? Because I know Dr. Molina did not use that term, but I prefer telling you why they are called the microreceptor and donors, because you can see what happens. You can see who adds to who. That way it's a lot easier, right? Acceptor means that I'm getting attacked, which means that the carbonyl is called the microdonor. Anyone called Michael here? No? Oh, Mike, right. I'm so used to calling you Salu anyway. Okay, so base comes in to protonate, deprotonate. There's proton here. I honestly don't know why I showed the mechanism thing at the bottom. It's really not necessary. But don't forget, it's reversible. What we have, oops, is this here. All right, so we have a nucleophile adding to our electrophile, or rather our microdonor attacking our microreceptor, right? So this is going to collapse down. Our microdonor is going to add to the beta position, pushing this to form an enolate. Right, so we are forming this carbon-carbon bond here. Okay, and then when we pronate it, well, you should know what the outcome of that reaction is from here. Right here. So we have lost the double bond. Okay. So microdonor, microacceptor. The next example is also another form of a microaddition. So this time, don't forget, when you have, let's say, a ketone versus an ester, where is the carbonyl going to form at? In which direction? Towards the ethyl or towards the ester? Well, technically it will, but that's why we have this step here to kind of stop the deprotonation process. Okay, so my question again was, in which direction is the enolate going to form? This way in black or this way in blue? Yeah, then you're going to end up with a case, David, of the electrophile adding to nucleophile. And that itself, if I were your grader, I would give you straight 0 because it tells me you don't know your concept at all, right? So is the microdonor always the ketone? Yes. The microacceptor is always the alpha beta unsaturated carbon, basically. So yeah, that's why I'm really strict with you with all these things, because you need to have your concepts down. And of course, the reason is if you really fumble in the exam, at least if you have your basic concepts, your examiner can see that and give you partial credit, right? If you do stuff like that, for example, it shows the examiner that you don't even know anything, right? Like you don't even know what your nucleophile is, you don't even know what your electrophile is, right? So don't do stuff like that. At least know the concept so that you can get yourself partial credit. Okay, so remember, as far as possible, you want to form towards the ketone, not the ester. But it wouldn't matter actually in this case. But if it comes down to a case where it matters, which I can't really think of it right now, just take note. I'm going to form it in the direction of the ketone using Naomi and her homies. Proton here. Okay, and this is a 1,4 addition, right? So this is my Michael what? The carbonyl is the Michael. Yeah, Michael donor. So that means that this would be the Michael acceptor. Okay, Michael donor adds to Michael acceptor. Oops, don't forget your formal charges. Oops. And of course, go ahead and add this step 2, which I forgot. So what we have would be this step here. Right here, and oops, let me go here and do this. So this here should be negatively charged right here. Okay, and then when we protonate it, we get this product here. Oops, sorry, should be ET. That's our product. You will not encounter a case with two sets of alpha betas. Or at least from what I've seen, from what I've experienced, there's never an example where you come across two. So I wouldn't worry too much about that because honestly, I don't have an answer for it either. Don't overthink it, okay? Yes, so right here is the beta carbon. So let me draw it out here. This is the alpha. Whoa. This is the alpha and this is the beta. Well, the one above, yes, I had it switched, but I added it to the right place though, so it's fine. Thank you. Yes, for a micro addition, it's always the beta carbon. And does anyone remember why? I just said it like maybe 5-10 minutes ago. Because of this resonance, right? We form the electrophilic site at the beta position. Very good. Okay, this reaction I'm going to talk about now, the Robinson annulation. Unfortunately, the Robin does not have a head, but it has pretty blue eggs, right? It's a really popular reaction if you catch my drift. I think just about every exam 3 that I've seen has this question in the mechanisms, okay? If not the mechanisms, definitely predicting the products or reagents, but not really in retrosynthesis. Okay, the key point here is that you need to have a 1,3-diketone. Whoever is that, please mute your mic. Okay, and you need to have a methyl vinyl ketone, MVK. So Robinson annulation is a form of mycoaddition if you actually look at it, right? Because we have the 1,3-diketone as a mycoacceptor, and we have our methyl vinyl ketone as the myco donor for the 1,3-diketone, and the methyl vinyl ketone as the mycoacceptor, right? So I forgot to put heat here again. I don't know what's wrong with me when I did the slide. So please watch out for that. Okay, and what you're forming, well, annulation means ring formation, orgo. See, more rings. We are forming this product here with that carbon bond there. Don't you think it looks so funky though? How does the one on the left becomes the one on the right? First and foremost, we are getting rid of one carbon and pushing it to the end, and we somehow end up with an alkene in there, right? Yeah, so more rings, okay? And then the same thing for here. Well, you can simplify this by writing it this way. Right, so everything else remains the same. What we have is this now here. Most times, you're always forming a 6-membered ring. Okay, 6-membered ring in the form of how many carbons? 1, 2, 3, 4. 1, 2, 3, 4. There we go. Okay, so anyone here remembers the driving force? As far as those who have come from my office hours last week, I gave you a little story, right? What was my New Year's resolution this year? To get rid of what? Toxic people, right? And Naomi's resolution is to get rid of the toxic host. Exactly. So you have to be kicking out an alcohol at some point in your mechanism. If you are not kicking out any of this host, right, you are not doing it right. By the way, 10 out of 10, I would highly recommend getting rid of toxic people. I did that and it was amazing. It changed my life. Okay. So let's see how she's gonna get rid of her host. And also what makes Naomi a basic kind of bitch this semester is the fact that she's what? Reversible, right? I cannot stress enough how important it is that you show the mechanism as a reversible one in your mechanism. Okay, so I'm gonna, okay, do you want me to do the one at the top or the one at the bottom? Why, just because it looks harder? All right, so the one at the bottom, we have 1,3-diketone, right? Don't forget our alpha hydrogen here. So Naomi, she's gonna come in to deprotonate the carbonyl. It doesn't matter which carbonyl you form, and this is the reason why she's such a basic bitch, because she cannot decide what she wants to do, so she's irreversible. Well, she's reversible. She goes back and forth, right? Right here. Okay, so we have our enolate, and now we can add on to our 1,4 addition, or 1,4 adduct. Ooh, where have we heard that term from? Do you remember? 1,4 adduct. Okay, so lone pair collapses down, and where are we adding to? The beta position, right? Good job. Right here. Right, so the 1,4 addition, 1, 2, 3, 4. Oops, I'm not using the same color. Okay, is right here. 1. Oops, it's right here. 1, 2, 3, and 4. Can you guys see that? Okay, so this is what we're adding to. And now, ask yourself, intuitively, you should be able to tell yourself that there's a nucleophilic attack that's coming your way, right? You have to form a ring when the lone pair collapses down and your enolate attacks here, the carbonyl, right? But here's the thing, is this ring that we're forming favorable? It's gonna be, it looks like to me, it's gonna be a 4-membered ring, right? It's not gonna work. Nature does not want that, right? So you're gonna encounter this thing called a proton transfer, where you're just gonna form the kinetic enolate. So you just have to show this term called proton transfer. What we have here is, oops, I don't have enough space. Okay, what we're gonna form is this here. Okay, so we form the kinetic enolate from the thermodynamic enolate. Okay, and the reason why we do that is because we get the most number of member rings. This is where we get our 6-member rings. So our lone pair can now collapse into a carbonyl, causing our enolate to attack the electrophile down there. Yeah, you can write proton transfer is susceptible. If you really do have to show error pushing, you just have to show this stuff here. Okay, so, hey, when we have, if we were to stick to this configuration that you see here, right? we are going to end up forming a 4-membered ring. One, two. No. It's a 5. 1, 2. Okay, let me draw the carbons here. 2, 3, 4. And then, shoot, I'm getting a brain fart. I'm sorry, guys. Okay, the point is we cannot form a 6-membered ring, and that is going to be unfavorable. When it's, remember, as you want to form as many membered rings as possible, and 6 is the sweet spot for anything. So like, it's like Goldilocks, right? 4 is too little, 7 is too, 5 is too little, 7 is maybe too much, 6 is right in the middle. So in order for me to be able to do that, I will have sort of a proton transfer where I'm just going to redirect that alkene here that you see right here, that enolate is just going to move its position. Okay, you just have to show that and proton transfer, and you will be able to get B. You just know that it happens actually, because for the most part, you can just show this step, double arrow PT, and you're good to go. So what you're forming is the kinetic enolate, and now you can form your 6-membered ring. So we have our alkoxide here. Okay, then what we have here would be a carbonyl right here. Okay. So we have a carbonyl. Do we have a step that says we're going to give it its that we're going to give the proton to it? Okay, I'm just going to do this here. Okay. We don't, right? We don't have any. We don't have ammonium chloride or a hydronium ion in there. So where do you think it's going to grab a proton from? It's going to find it from the alpha position right here. So draw your arrows to grab that proton. We have our enolate. Oh, and do you see the hole coming in already? Right? So it doesn't like that. So what's going to do? The carbonyl, the lone pair is going to collapse, forming my 1 alpha, beta unsaturated carbon, and then the hole is driven off, right? And because of that, well, remember, toxic people are what? They're hard to get rid of, right? If you have been clinging on to that one X that's been toxic in your life. So I'm gonna help Naomi do that. And how are we gonna help Naomi with that? Yes, we're gonna use heat to drive the hose out of her life. And there we have it. Okay. Bye-bye, Ho. Make sense? And do you notice the direction of the arrows? Once it's kicked off, right? Once alcohol is kicked off, you do not bring it back into your life. So that's why it's one directional. Okay, so it's akin to deleting that toxic excess number of yours in your cell phone. You're just going one way and never looking back. Okay? Highly recommended. Can you pronate with HOME? No. Yeah, good. Never forget this. That's why it's so important. I had to come up with a story for it, just to cement it in your head. Yes, once usually an alcohol is kicked off, well, even though it favors it, but that's why we need to put heat to keep forcing the alcohol out of the molecule, right? Even better still, oh, thank you, Erica. When we have a gas, right, think about what happens. I mean, I have never worked in a lab, but kind of like in the sense, common sense tells me that once you form a gas, it kind of bubbles out of solution, right? When, especially, okay, the only lab experience I have is orgo lab, and whenever you form a gas, you see bubbles coming out, right? You cannot put the bubble back into the molecule. It doesn't make sense. So that's why it's irreversible from there. Why can't we use HOME? Well, HOME is just a solvent, right? So we have never really touched with HOME for this entire chapter. It's just there as a solvent. The star in here is Naomi. Don't use HOME or she's not going to be happy. Really? That's how it's raining from set 10. Let me see. So they grab the proton from alcohol. It grabs that proton from the inside. Okay, let me go and check on that, and I'll make the necessary updates. Okay. Again, you're probably going to get a while you're sleeping email from me tomorrow, and if you do, if I'll have to go and check my notes and update it. Okay. Every point counts. Yeah, I agree. Thanks for letting me know. I'll check it out. But just look for the final uploaded version tomorrow morning when you wake up then. Okay, but the general idea is this here. Well, at the end of the day, you're still driving out the alcohol, so that still stays, right? You might just take a little bit of a longer route to get there, but as long as you get the alcohol, you're fine. Yes. Speaking of live lessons, I hope you guys are practicing self-love, self-care, or whatever it's called, right? Do something fun. Do something that gives you a mental break. Don't stress too much about orgo. It's fine. Okay, so with that, I am gonna go into the quiz. Okay, I had so many emails this week on quizzes, but it really sucked on my end that I couldn't answer them. So let me just go through it right now. Yeah, social distancing is hard. They just imposed a lockdown in Singapore, but they didn't want to use such a harsh word like lockdown, right? Because it kind of scares people. So they called it a circuit breaker. And well, I'm seeing it as a lockdown because from tomorrow onwards, I cannot go anywhere anymore. So I definitely had to be isolating myself at home. Okay, let me open up the quiz. Okay, so I'm gonna do selected questions regarding the quiz. So let's look at this one here. I think there were 6 different quizzes, right? Well, I have the quiz bank with me, so I don't know how your TAs assigned it, but what I'm working off is the bank. So it's not a particular quiz, but if you don't have this question, it's always good to have extra practice too anyway, right? Yeah, I know. I hope they find something, right? Isn't it frustrating that we're all in this right now? Okay, what kind of base do we have here? Thermodynamic base, which means that it's going to find which proton? The one on the left or the one on the right? More substituted one, exactly, the one on the right. And do I do this? No, exactly. Potassium hydrides, or rather hydrides in general, are not reversible bases. So we form our enolate right here, right? And what we have is our substrate. So we can draw our arrows going down in here. Oops, sorry, what am I doing? It's going in here, kicking off the leaving group to form, oh, that was horrible, sorry. This year, right? Because on the step before, I'm sure you guys would know, has the carbon there, right? Sorry, it has the double bond there. So it's going to be this year. Right? So then we just reduce it down with hydrogen. So the key point here is what? The thermodynamic base, right? Okay, let's look at this one here, which is on your problem set. Oh, sorry, it's not the 7-membered ring. Anyone here hates 7-membered rings like I do? They're so annoying to draw. Oops. Okay, don't forget, there's heat here. So we are forming a what? Typically an alkene, exactly. Okay, so let me show you the mechanism. I'm only going to show the mechanism for the first step because the second step and the third step is pretty much an orgo 1 type of reaction. Okay, so the mechanism that I'm going to go through is also what was on some of your mechanism questions, right? I just want to make sure that you guys look at it, understand this. I do apologize. I was unable to incorporate this into my reviews. There's really just so much I can do, right? So I just felt like, okay, I'm not gonna cover it. And it turns out that it was on your quiz. So trust me, I feel bad about it. Okay, so what we have here is a methyl, right? So carbonyl attacks first, right? Because we have what kind of a reaction condition here? Yes, it's acidic. So a pronation process starts first. right, in the form of a, so if I could deuterated hydronium ion. So it goes here. And is this reaction reversible or irreversible? Do I keep the reversible arrows there? Yes, good. Okay, so we have our proton. Let me go ahead and do this. What is this chapter that we're talking about, people? Anyone remembers the name of this topic? Alpha carbon chemistry, right? And what are we forming? What do we need to form in our mechanism if not we're doing it wrong? Yes, we need to form enolates, right? So the only way we can do enolate formation is through a deprotonation of that hydrogen there to get us the acidic enolate. Okay. Then do you see that this process is just going to repeat itself? Because after I grab that proton, right, it's just going to go and do this. Well, E2O, right? It's going to go and grab this proton here. So carbon, deuterium, and hydrogen here, right? Okay, and this process is going to repeat itself exactly. Right? Did your professor say they can do 3 times? Because that's what I would do. Did Dr. Driver say that? Okay, do you want to tell me? Do you remember? Well, let's just go ahead and say, yes, it should be okay. And what we have here eventually would be this here, right? Oh, she wants you to write it out? Okay, well, let's write it out then. So same thing would happen again. This is already protonated, so another water, deuterated water is going to come in. And what we are forming here is not really an enolate, but rather an enol. A deuterated enol. Okay, and then you're going to come with a D3O plus again. Form this, grab the proton. Right here, right? So we have 2 deuteriums already. We need 1 more. So again, water is going to come in. Sorry, deuterated water. Or the acidic protons that come in here. Oops, sorry, what am I doing? Should be this here, right? So we have our last proton. That's going to get deprotonated here. Okay, and then last step. The last proton is now going to get attached onto the carbon. So we have a CD3 functional group here, right? With the OD plus. So water is just going to come, sorry, not water. Deuterated water is just going to come in to grab that proton. And then it pushes that reaction to completion. Can I just put PDT? I'm sorry, I don't have space. Which is the product of product one. Okay, so product one is going to be here. Okay, now we're going to reduce it down using lithium aluminum hydride, but notice that we did not put a second step that's usually associated to it, which is what? H2O or H3O plus, right? The bottom step, step 3, is a separate step on its own because you're going to see why. Okay, do you guys remember back in Orgo 1 when we had this here? What was the product of this reaction outcome here? Back in Orgo 1. Yeah, you get an alkene, right? It's right here. So this is the same type of concept where you're gonna have sort of like an alkoxide, right? CD3. This is step 2, which brings us to step 3. And what does step 3 do? It's the same thing, right? It takes off the alkoxide and it gives an E2 kind of reaction, which you don't need to know the mechanism because that was not taught. Only for product 1 do you need to know how to draw the mechanism. So what you have is therefore this answer. Clear? Okay, I'm going to leave it here if you guys need more time to copy. Okay, next one. Yeah, I'm gonna go through the reverse in a bit. You know what? Actually, might as well talk about the reverse while we're on this topic now. All right, so, okay, well, some of you had this, right? And instead of using deuterium, you get the reverse, H2SO4 and H2O. Truth be told, did anyone here have their problem sets open with or the notes open during the quizzes? I'm not gonna rat on you. I mean, it's not wrong. Yeah, right. That's why I think they made it harder. Okay, so we have this here, right? So first things first, we need a protonation step because this is acidic. So we're gonna get a proton. And it's reversible. Okay, so we have this here, and now the reverse happens, right? Water is going to come in as a nucleophile to grab one of the deuterium, because remember, we need to flex our enolates. We need to show that. Okay, and then what happens now, because we're dealing with water and sulfuric acid, OH2SO4. Okay, so it's going to form carbonyl again to grab the proton. So we get our first hydrogen onto our molecule. One's deuterium, one's hydrogen, deuterium, deuterium. Yes, it should be OH. Thank you, Kay. Okay, so OH plus. Okay, can you guys kind of guess what's going to happen next? It's going to repeat, right? So another water molecule is going to come in. Sorry, I got the wrong proton. Okay, what we have now is hydrogen atom here. Okay, there we go. Right? And again, we need to make that hydrogen, right? So same thing. As you can see, I'm not gonna do all four, but you guys should do that in the exam. For the sake of time, I'm not gonna do it, right? So OH plus hydrogen, hydrogen, deuterium, deuterium. Okay, so then you're gonna repeat again 2 more times. But remember to show in exams. And what you're gonna have is this here. And finally, you're gonna get water just coming in to grab the proton. Right here. Okay. No problem. Okay, so all the hydrogens in the alpha position are gonna become deuterium, but if you're going to go back, it's gonna be what do you call that? All deuteriums become hydrogens. Last step, just single arrow. Well, technically, it's an equilibrium, so yes, it should be reversible all the way. Though I do have that habit of just showing one arrow when we're forming the product, but because by concept, this is an equilibrium type reaction, right? So yeah, for the most part, you guys all had that. Okay, this question here. The key showed 2. So I'm just gonna do that. But if you guys remember the way I do it, it's always showing 1, right? And that's fine. I think it really doesn't matter in the last step, as long as you remember to show it reversible all the way. Okay, so some of you had this on your quizzes as well. Yes, please show all your hydrogens, okay? Or at least the ones that are participating in the reaction. Okay, who here stumbled with this? Because this here was on my notes. So if you had my notes for the quiz, you would have seen the exact same thing. But instead of forming a 6-membered rings, and instead of forming a usual 6-membered ring, this is forming a 7-membered ring, right? And I did this twice, one in my spring break review and one in on last week's review. Okay, so don't forget you have an acidic proton here. To get that. And now because we're using a reversible base, we have to show the reversible mechanism. Right? And then bromine, our 7-membered ring chain. It's going to come as a nucleophile attacking the electrophile. Sorry guys, give me 1 second, let me close the door. Much better, okay. So then we have now one, two, three, four, five, six. Okay, so we have 1, 2, 3, 4, 5, 6 with a leaving group. So then the process is going to repeat itself. Naomi and her homies grab that proton. Am I going too fast? Okay. Right, so then the process repeats itself. It's going to go for this electrophile to form a ring here, right? So what we have is our prime product being a 7-membered ring. Oh, this test is the worst of everything. Bicyclic, 7-membered rings, deuterium. Oof. Must have been painful for you guys. Okay, so that's our answer. Do you remember the example that I did before? I put an ester in there and I reduced it down with lithium aluminum hydride after, right? So that's the same example, pretty much. Okay, let's do some predicting the reagents. Because everything else is pretty much the same. Oh, right? I mean, you're predicting the products was one of these variations that I did here. Is there anyone in particular that wants me to go through a question that's not covered here? No? Okay. Let's do some predicting the reagent problems. So here's the thing. When I saw the quiz, I felt that if you could do predicting the reagents, you should be able to do well in the retrosynthesis, right? So what we have here, what's happening? It's kind of hanging. Okay, there we go. What we have here is our bicyclic methyl with a ketone. Okay, and you're asked to predict the reagents for this product here. There should be hydrogen. Then that one here should be something like that, right? You guys had this on the quiz. Okay. So let's ask ourselves first, what's happening here? We're pulling our bicyclic apart to make it planar, right? Remember, I've gone through this many times already. So I hope you guys still, okay, who here still struggles at this point? Be honest with bicyclic compounds. No, you're fine. Thank you for telling me, because then I want the three of you to sign up for my office hours this week so that I can go through it with you guys in detail. Okay, you need to understand this. It's super important. All right, even if you don't register, I'm gonna send you the link to my office hours anyway. Better be there, because I'll be going through bicyclics on Tuesday. Okay, I'll briefly go through it today. So what we have here, well, we know that we have to cleave this double bond here, right? I could give this to an Orgo 1 student and he should be able to do it as well. What do you think that step is? Yes, it's going to be ozonolysis, exactly. So with ozonolysis, we know that, okay, the step before this then has to be this here. What we have is our carbonyl with that long R chain, right? Okay, so we can sort of bring it together now and ask ourselves what changed from here to here. We saw that there was a chain that was going longer, right? But where is the chain going longer at? The blue side or the red side? It was on the blue side, which means that this is the kinetic or thermodynamic position. Exactly, it's a kinetic position, so we have to use LDA, right? Because LDA is the only kinetic base that we've seen so far. And how many equivalents are we going to use? .05, good. Okay, 1.05 equivalents. So what we have is, how many member chains are we adding? We already have a methyl here, right? So we are adding an additional 1, 2, 3, 4, right? Okay, so we are adding an additional 4. Okay, here's the thing though. What would happen if I were to do this here? You would favor an E2 reaction, exactly, right? So just go ahead and protect it by making it a Lillet here. which means that I would have to reduce it down to an alkane, right? Right here. And can I use H2PDC? Why not? Exactly. We need to retain that olefin that's in the ring. We cannot get rid of that because we know on the very last step, we are going to use that for ozonolysis, right? So we have to retain that. That's why we know that Wilkinson's catalyst is not going to cut that out, right? It's only going to cut the one in the chain. So it has to be specific here. And then finally, we can use ozonolysis. Okay, because in the product, you see here, it's reduced down into alkene. So what would happen if you did ozone before reducing it down, Sangwoo? Do you see that there's also an alkene on the chain that would also get cleaved? So you cannot. You need to retain that part. Okay. So the reason why we have an alkene in step 2 is because if we don't have the alkene, and go ahead and did this here, right? And we had an enolate. What would happen is that, well, instead of having a nucleophilic attack, we're going to favor an E2 reaction instead. So in order for you to avoid doing that, you will have to you would have to put in a allelate position there. You have to put an alkene in there to protect it so that you don't end up with that E2 thing going on, and instead you're going to get that addition product. Oops. Here. Okay. So there's no, well, for phenols, you don't have to protect it because don't forget, phenols by default are already protected with the alkene there. So if you had a phenol, you don't have to, you can just put phenylbromide, that's fine. Okay, what's another way to write ozonolysis? Osmium tetroxide in NMO. And then we break it out with what? Sodium periodate. Good job. Okay, yeah, probably just gonna put acetone in there. That's fine. I don't have space, but if you guys know, that's good. Please just put it in there. So bring it all together. We have this step going to this step. So this is step 1, 2, step 3, and then step 4. Wow. Oof. Okay. All right. So this was a more of a retro problem, which some of you got it, right? So if you chose the OSO4 route, it's step 4 and 5. Yeah, that's correct. Okay, let me see. Is there any other questions? Okay, some of you had this here. Okay, some of you had this. but instead of using the kinetic base, you had a thermodynamic base, which is this here. So maybe we had this here, right? So the steps are largely the same. The only difference is what? First step, yeah, you're gonna use 0.95 equivalents for that reaction set, or you could also use potassium hydride 18.6. Right, these two might work, and everything else is pretty much the same. Okay, but right here, what we have here is a thermodynamic, oh sorry, this is a kinetic base. This here. Thermodynamic base. Okay, let's go ahead and do retrosynthesis. Yeah, so I'm so confused because the retrosynthesis is literally the same thing as predicting the reagents, right? So let me do one example, but instead of using a 5-member bicyclic compound, they gave you a 6-member ring, right? So right here. Okay, this is your product. Okay, so this is what we have. Please remember that OHC, CHO, that just means an aldehyde. And this is your starting material. But you have a 6-member ring now. Okay, so I'm gonna do only one example because everything else is pretty much the same. You guys just have a slight variation of this, but the only thing that changes here is the base, right? Okay, so we know that we are adding what? Are we using a thermodynamic or a kinetic base? Thermodynamic, very good. We want to get rid of this proton here. So we're going to use potassium hydride, right? Step 1. Thermodynamic conditions. So we're going to also add in our bromine with our leaving group, right? But do we stop here? Can I just do this? No, remember, it has to be in a Lillard position. You need an alkene for it to work, right? Okay, so then what we have is going to be this now. Okay, and then they needed you to do step 2, which is to reduce it down to an alkane. And how would you do that? Again, can you use Wilkinson's catalyst here? Yeah, you can, right? Because you cannot use palladium on carbon because that tri-substituted alkene is going to get reduced down as well. So we want to avoid that. We want to protect it. So that's a good thing about Wilkinson's catalyst, right? It's chemoselective like that. So it's okay if you don't remember. If you don't remember the what do you call that? Name for Wilkinson's catalyst, the molecular formula. You can write Wilkinson's catalyst. That's fine. Where is this in my notes? Organometallics, right? Remember when we were doing quick maths, which we're actually going to do again next week, by the way. 2 + 2 is 4. -1, that's 3 quick maths, right? So we have the alkane. Right here is the product that we have, the intermediate. And then we're going to open it up into a 6-membered ring, right? How does this look like right here? It's a 6-membered ring here, which is going to be right here. What we have is sort of a boat configuration type, right? Which, you know, then can become a chair because chairs alternate between boats, twist boats, before going into cyclohexane, right? So this step is going to be ozanolysis again, but they gave you 2 steps. So that means you probably have to use the osmium tetroxide, right? Right. This is also another acceptable condition if you were familiar with it. If you were not, that's fine. Just go ahead and use NMO and acetone. You should be able to get away with that. And then sodium periodate to finish it off. Okay, so that was really simple. Why can't we use O3 and DMS in the first step? Let's see. Okay, well, I'm just following numbers here, but you should be able. Let me see. Well, if you use O3 and DMS in the first step, then you're going to end up having 2 ketones right away. Yes, that's correct. That's fine. But you are not going to, I don't think you're going to line up with the numbers and you might get a little bit of points taken off. So I think if you swap the ketone step in the first and the last, that might not be as hurtful as if you would have put it on the second step, because you can never put ketone on the second, ozanolysis on the second step, because look here, this alkene is also going to get cleaved. So you have to be careful, right? Alkenes are very sensitive to ozanolysis. That is one of the core reactions that we learned back in Orgo 1. Remember ozanolysis, the heartbreaker, right? Because ozanolysis breaks bonds, it cuts them in half, right? So you cannot use ozanolysis on step 2 at all. That would be straight up 0. So you have to be very careful. The quiz is really tricky like that, right? It's kind of forcing you to apply a lot of conceptual knowledge and not just copying off your notes, because, well, I think that's the point. they want you to apply your knowledge in there. So please try to understand what's going on. Also, for this week's officers, I'll be sure to incorporate more. Sorry, for next week's amine review, I'll be sure to incorporate more bicyclic compounds, just to give you the exposure. There's really nothing shameful in admitting that you're still struggling with that. It's okay. It took me forever as well. That's okay. but you really need to understand it going to the exam, okay? I didn't, and that's why I got points taken off. Exam 3 is typically the hardest in nature for any orgo exam. So please watch out. Now, especially that it's so-called quote unquote take home, open book, open notes. Be very careful that you can see questions like that, right? I won't lie to you. My exam 3, I got a 36 out of 125. Okay, but that was because I was not a good student then. So with enough preparation, enough studying, and understanding the concepts, you will be able to do way better with than me. Which is why for exam 3, I never do the push-up bets with anyone. I'm not about to do like 90 push-ups for someone. Yeah, so no. Okay, so while it's 9, this brings me right to the end of alpha carbon chemistry. Please go and study the notes again, especially this. Oh, since that didn't come out on the quiz last week, I won't be surprised if one of your questions end up being the Zimmermann transfer. Well, only one person made that bet with me, and I really did it for that person. So, and also one other person did it with me, but he got the same exact score, so we kind of squared up from there. Oh, you didn't claim that for me? Damn. Okay. Well, when next time you see me then. And for those who, so if you're done with alpha carbon, feel free to leave. I will stay behind for maybe just a little bit more to answer questions pertaining to amines, especially for those who are taking the quiz tomorrow. I hope the alpha carbon has been a fun ride for you guys. You're welcome. Yeah, you guys take care, okay? Wash your hands. Stay safe. Yep, see you Tuesday. Okay, so that one, wait, is it the one with sodium cyanoborohydride, Faith? Because if it's that question, thing is, your Melina section have not gone through it, so I'm not too sure if that's going to be on the quiz. Okay, let me see. Does it have a transition metal catalyst? Or is there a particular problem on the problem set? Oh, so um, okay, that one there. Is it conceptual that you're not understanding, or? Hey, because I think you can kind of get it mixed up with alkanes. So this is hexane. I'm not gonna draw it out, but okay. So this is the problem here. Okay. If I remember correctly, this is not a typical question that they would ask for a mechanism, but let me just go and check real quick. So I've never really seen this being asked on mechanisms. Yeah, I've never seen this mechanism before. Did Dr. Driver go through it? Yeah, so if you did not go through it, then you won't need to know how to draw the mechanism. Because I think there's some reactions in this chapter where they just assert you the way the reaction works, and this is probably just one of them. So it goes through this intermediate. Right, before forming, well, you're just reducing it down after. Yeah, so this is, yeah, sorry, I can't answer that.